this module, you will learn the definition and properties of conditional probability. When a coin is tossed, the maximum number of possible outcomes is 2. We will get either a head or a tail. When 2 coins are tossed simultaneously, the number of possible outcomes is 4. Similarly, the number of possible outcomes increases to 8 when 3 fair coins are tossed simultaneously. The set of all the possible outcomes of a random experiment is called a sample space and is denoted by S. Each outcome in a sample space is called a sample point. So, the sample space for the experiment when 3 fair coins are tossed simultaneously is the set of all the possible outcomes. Here, each sample point is equally likely. Since the coin is fair, the probability of each sample point in the sample space is 1/8. Let A be an event that at least 2 tails appear. That is, 2 or more than 2 tails appear. Then, the sample points in event A are HTT, THT, TTH, and TTT. The probability of event A is the sum of the probabilities of its sample points, which is equal to 1/2. Consider another event, B, where the first coin shows a head. The sample points of event B are HTT, HHT, HTH, and HHH. The probability of event B is equal to the sum of the probabilities of its sample points. This is also equal to 1/2. Observe that the sample point HTT is common to both the events A and B. This implies that event A intersection B has one element, that is, HTT. The probability of event A intersection B is 1/8. We just calculated the probabilities of events A and B, considering that they happen independently. Suppose we have to find the probability of A if event B has already occurred. In such a case, the sample space for event A will be the set of sample points of event B. In other words, event A is a new random experiment for which the sample space is the set of all the favorable outcomes to the occurrence of event B. And event A is the appearance of at least 2 tails. Therefore, the sample point of B favorable to the occurrence of event A is HTT. The number of sample points in the sample space of event B is 4, and all are equally likely. Therefore, the probability of each sample point is 1/4. It implies that the probability of event A is 1/4. Here, the probability of event A is called the conditional probability of A given that event B has already occurred. This is denoted as shown and is read as the probability of A given B. Observe that the sample point of event A, given that event B has already occurred, is common to both event A as well as event B. Or, the outcomes of event A are the sample points of event A intersection B. Thus, the conditional probability of A given B can also be written as the number of elementary events favorable to event A intersection B divided by the number of elementary events favorable to event B. This is equal to the cardinal number of A intersection B divided by the cardinal number of B. On dividing the numerator and the denominator by the cardinal number of S, we get the probability of event A intersection B divided by the probability of event B. Mathematically, conditional probability is defined as if A and B are two events of the same sample space S, then the conditional probability of event A given that event B has occurred is given by the probability of A given B is equal to the probability of A intersection B divided by the probability of B, where the probability of B is not equal to 0. Let's apply this result to find the probability of the previous experiment in which the sample space and events A and B are given as shown. Here, we need to find the probability of A if event B has already occurred. Now, event A intersection B is the set of the sample points common to both the events A and B, which is HTT. Now, the probability of the occurrence of event A intersection B in sample space S is equal to 1/8, and the probability of the occurrence of event B is equal to 4 divided by 8, which is equal to 1/2. Therefore, the probability of A given B is equal to 1/8 divided by 1/2. On simplification, we get the probability of A given B as 1/4. Note that the definition of conditional probability can also be applied in a general case, where the elementary events are not equally likely. Let's now discuss the properties of conditional probability. The first property says, if A is an event associated with sample space S, then the probability of S given A is equal to the probability of A given A, which is equal to 1. We know that the probability of S given A is equal to the probability of S intersection A divided by the probability of A. Since A is a subset of S, S intersection A is A. Thus, the probability of S intersection A is equal to the probability of A. Therefore, the probability of S given A is equal to 1. Next, the probability of A given A can be written as the probability of A intersection A divided by the probability of A. We know that A intersection A is equal to A. Thus, the probability of A divided by the probability of A is equal to 1. Hence, the probability of S given A is equal to the probability of A given A, which is equal to 1. The next property says that if A and B are two events of sample space S, and E is an event of S such that the probability of E is not equal to 0, then the probability of A union B given E is equal to the probability of A given E plus the probability of B given E minus the probability of A intersection B given E. Let's consider the left-hand side of the equation. By the definition of conditional probability, this can also be written as the probability of A union B intersection E divided by the probability of E. By the distributive law of union of sets over intersection, the numerator becomes the probability of A intersection E union B intersection E divided by the probability of E. On simplification, we get the probability of A given E plus the probability of B given E minus the probability of A intersection B given E. This is the right-hand side of the property. Hence, the property is verified. We know that for two disjoint events A and B, A intersection B is a null set. This implies that the probability of A intersection B given E is equal to 0. Therefore, the probability of A union B given E is equal to the probability of A given E plus the probability of B given E if A and B are disjoint sets. Another property says that if A and B are two events of sample space S, then the probability of A complement given B is equal to 1 minus the probability of A given B. We know the probability of S given B is equal to 1. This implies the probability of A union A complement given B is equal to 1, since union of A and its complement is equal to S. Events A and A complement are two disjoint events. Thus, we get the probability of A given B plus the probability of A complement given B is equal to 1. Therefore, the probability of A complement given B is equal to 1 minus the probability of A given B. In this module, you learnt that if A and B are two events of the same sample space S, then the conditional probability of event A, given that event B has occurred, is given by the probability of A given B equal to the probability of A intersection B divided by the probability of B, where the probability of B is not equal to 0. If A is an event associated with sample space S, then the probability of S given A is equal to the probability of A given A, and both are equal to 1. If A and B are two events of sample space S, and E is an event of S such that the probability of E is not equal to 0, then the probability of A union B given E is equal to the probability of A given E plus the probability of B given E minus the probability of A intersection B given E. If A and B are two events of sample space S, then the probability of A complement given B is equal to 1 minus the probability of A given B.